My name is Feyzi Bagirov. I'm a faculty at the Harrisburg University and the data science advisor to metadata.io startup, San Francisco startup. My co-presenter unfortunately could not make it today. Tatiana Yarmola, she's the VP of Governance and Review at JP Morgan. And the topic of today's presentation is Analysts' nightmare of or laundering massive spreadsheets. Just by quick show of hands, how many of you are web developers and how many of you are web developers? How many data analysts? How many are both? Okay, so we got a couple of both, good. So today we'll talk about the topic that is most important, as I will show you later, in the data analytics process, data cleanup. We're going to cover the Excel a little bit because, believe it or not, it's still the most popular BI tool in the world. Now that we have all that open source, it's still the most used and popular BI tool in the world. We're going to dive into definition of dirty data and the methods that you can use to clean it up. And finally, we're going to look at the use case that we came up with using the Fitbit data. Everybody is aware what Fitbit is? So it's a step meter that can measure your steps, your heart rate, etc., etc. So Excel is still the king. Back in 2007, I used to work for a big PLM software company in North Carolina. And at one day, they decided to implement the business intelligence. Back in 2007, data science was 1 year away, and business intelligence was the most popular thing to acquire data and analyze it. So the company acquired business objects, very expensive software. They invited the trainers who gave the selected employees 2-day training, and that's it, and he flew away. In a couple of months, and I attended that training as well. In a couple of months, I was asked to create an instance of business object report, and I realized that I don't even know how to use it. So I came around the company and started asking people who were at that training with me, can you show me how do you use it? And I figured out that they had no idea either. So the reality was that companies, and it's not just the case for this company, companies around the world are still, no matter how expensive your software is, most of the employees will import the data into Excel, will do the manipulation in Excel, and then they'll just try to push it back into the software and make it presentable. So, and then according to the Gartner, Excel is still most popular BI tool in the world. This is the magic chart from IDG that shows that Microsoft is both within the leader and the visionary, has the advantages over the other tools. And of course, there's a question on if you're an how do you do data science if you're in Excel, if you're working just with Excel. So most of the data is still worked on in Excel. So everything, all bugs in Excel are also applicable to that data. So what is dirty data and how do we clean it up? So everybody's familiar with this bug in Excel, right? The initial 0. Unless you put some asterisk in front of the number, the Excel will easily truncate the front 0. So VLOOKUPs do not take duplicates into account. Copy, paste, or manual imputation create additional errors, and duplicates and nulls are overlooked. So the point is that when the data happens to be not as clean as you hoped it to be, serious errors can occur and reproduce through the spreadsheet work cycle. This is another chart from IDG that shows how much time in the data science project data cleanup takes. Everybody probably guessed that it's 60%. And I would say this is quite conservative because to my experience, it can take up to 90% of all time. Modeling is about 5%, maybe another 5 visualization, but most of the time is data cleanup, variable transformation is what's taking a lot of time. The cost. Harvard Business Review posted an article 2 years ago that said US loses $3 trillion per year because of the bad data. And of course, from statistical aspect, bad data is always giving you a bias danger. Because if you don't have a clean data, you're less likely to arrive at the truth than if you have a clean one. So some members of the intended population are less likely to be included than others. Results in a non-random sample of a population. Results can be erroneously attributed to the phenomenon under study rather than the method of sampling. So some of the common types of dirty data are missing data. That's the biggest one, and there are different flavors of missing data. Duplicates, outliers, multiple comma-separated values that are stored in the same column. Column headers posted as values and not the variable names, and also encoding. And given that Santo Domingo is a Spanish-speaking country, that could also pose significant issues. So let's just look at the 3 types of missing data. So the first one is missing completely at random. By the definition, if an event that lead to any particular data item being missing are independent both of observable variables and of unobservable parameters of interest and occur entirely at random. So basically it's a Wikipedia definition, but basically what that means is that the missing data is unsystematic. So as an example, if you're participating in the survey and you mailed your questionnaires out and all participants filled them out and send them back into you, some of them got lost in mail, that would be an example of missing completely at random. Missing at random. Again, another Wikipedia definition occurs when the missingness is not random, but where missingness can be fully accounted by variables where there's a complete information. An example of that would be a depression survey. Both male and female fill it out, but males will probably put 0 because they don't want to acknowledge that, we don't like acknowledging that we're depressed, that we're weak, so we'll just put 0, and that's actually will introduce the missing at random value. And finally, missing not at random value, it's the value that doesn't fall into the first 2 categories. And basically, missingless is specifically related to what is missing. So, as an example, a person doesn't want to take the drug test because that person, took the drugs the day before and he knows that he or she is going to fail. Some of the causes of dirty data could be mechanical error. So the typist just typed in something wrong. Business rule violation, a salesman wants to push the sales process through, and he skips the data that he should be filling about the customer address, etc., etc. Database mergers. You have AS400 IBM mainframe, legacy system that stores all the data, and you're trying to push all that into a newer Oracle system. Some data will be lost, some data will be imported incorrectly, etc., etc. So, most recently, Hadley Wickham, the British statistician, developed a concept of tidy data, and he first posted it in 2014 in the Journal of Statistical Software. So, bottom line of the article is that observation in every data set, observation should be as rows. Variables should be as columns, and 1 type of observational unit per table. So, meaning that if you have if you have a data set about the dogs that contain information about the dogs, about their owners, about their addresses, that's actually 2 observational units in one data set. So it sort of relates to the concept of normalization in the databases, where you have to break it up as much as you can. Maletic and Marcus also posted the general framework for data cleaning. So the first step is always define and determine your error types. Search and identify error instances. Correct the errors, document error instances and error types. And finally, modify data entry procedures to reduce the future errors. Which brings us to another important question, actually statement, that error prevention is far superior to error detection and cleansing, meaning that if you can fix it before it becomes dirty, then you should be doing that instead of keep fixing it all the time. To reinforce my previous statement, you can fix the data at the database level, manual cleanup inside the database, non-scalable way. At the application level, where it's more automated, you basically create a script when you, when your data sources are pretty systematic and you already know the typical errors that can occur there. It's easier to automate it by writing scripts. Identifying the commonly occurring problems with your data and the tasks to fix them. Once you identify the most common tasks related to your data cleanup, create scripts that you're going to be run on every data set. Okay, so to illustrate the issues, we selected a very simple data set. It's publicly available at this link. And basically, it's measures of steps and intensity and distances from some Fitbit users. They're all anonymous instead of users are IDs. And we also introduced the data quality issues because the data set by itself was clean, but the whole point is of this topic is to actually demonstrate how bad data can cause, malicious results, malicious output. So we introduced data quality issues into the data set by randomly replacing values with nulls and randomly added outliers. And the objective was to provide a simple example that illustrates how data quality issues may visibly affect results on analysis, and to estimate customers' height based on an average stride length and see whether results belong to an expected ranges. So in other words, by injecting the formula that was coefficient that was actually looked up on the defined by Fitbit, and we looked it up. We would attempt to calculate the height. Again, the height is not objective, but the data cleanup is objective. The tools that we used, obviously Excel, Python 3.6, we used Pandas, Panda library, and Jupyter as a tool. And by the way, how many of you are using Jupyter? Quite a few, okay. So we had 3 data sets. The first 2 were steps per minute and intensities per minute. Again, all the users were anonymous as user IDs. The steps per minute are pretty self-explanatory. The intensities are range from 0 to 3. So in Fitbit, intensity means that the lower it is, the lower your heart rate is. So in other words, if I'm walking towards the next chair or just walking back and forth to the wall, that would probably be 1. But if I'm jogging a little bit, that's going to go to number 2, and then 3 is when I'm running, perspirating, etc., etc. The third data set was daily distances, and you can see that there are several variables: sedentary active distance, light active distance, moderately active distance, and very active distance. So the quick and dirty height calculation that we had, again, to compare something, we need something before and the results after the cleanup. So Before cleanup, first of all, we merged these two data sets. That was an easy fix because they have the similar variables, similar IDs, so it's easy to merge them. And once that was done, we also added the distances data set. And we made some assumptions about it, but basically we created one large data set. So once we've calculated, and by the way, this is the code for that data set. So again, we're merging them by IDs. We also looked at the intensity that is more than 0. And then we introduced the formula that we looked up. And 5280, the 065 is so the number of steps, and 065 is approximate length of the step. And finally, we have the formatting line at the bottom. So once we got the results, basically we clearly had some outliers. So we had a person whose height was calculated at 3 feet, which is in centimeters, I think about 90 centimeters. We had one that was 13 feet, that's way too high, and 8.3 and 1.5. So again, we introduced those errors here, so just to show that the results can be way off. So step 2, we started with exploratory analysis. The first thing that we noticed is that the IDs in intensity and steps data set, which is supposed to be of the same type, they're actually of a different type. So in the intensities, it was an integer, and in steps, it was an object type, data object type. That was one issue that we had. The second issue was clear outlier. A maximum steps of 500 per minute makes a person walk about 8 steps per second, which is probably pretty high. The other issue that we noticed is that there's a lot of missing values. So the 75 percentile had zeros. When we tried to pull unique user IDs, there were clear difference. I mean, there were difference with 3 IDs, which was clear to us that it was the steps had duplicate IDs. So again, this just reiterates what was in the previous slide. Most values in steps for steps and intensities were zeros. Nulls, there were a lot of nulls in minute steps. Number of unique user IDs were different. And maximum number of steps per minute is 500. So some of the more observation that we had was that number of unique IDs matches minute intensities, and the sedentary active distance were mostly zeros, so we dropped it. So then we actually went on to cleaning. So again, we looked at some of the IDs that were not of the integer type, and we convert them to the integers. So we converted them to integers, and then we merged them with the intensities. So before the merge, if we would look at the length of the intensities data set, it would clearly have some extra data than the steps one. And after the cleanup, it was actually came pretty close. So we then started, this is the code to clean the data set up. So this function would convert the IDs to the integer type. This code will remove the duplicates from minutes and intensities. And finally, again, we're printing everything out to understand the numbers. The next step is to look at the nulls and outliers. So we had plenty of nulls, missing values, and some of the outliers as well. So let's talk a little bit about the types, or the methods rather, that we can use to replace the missing values. And speaking of which, outliers are also subjects to a lot of methods, because if you think about it, you need to do something about the outlier, and typically you would do the same thing. You would replace it with some random variable. So basically the missing values could be replaced by imputation, either single imputation or multiple imputation. So the single imputation has a lot of methods, and let's look at them in a little bit more detail. So the simplest method is mean substitution. So whenever you're missing 10 to 30% of your categorical data, let's say you're missing age, the easiest one the easiest method to use, probably if your business rules allow that, would be to replace that with an average for that variable. The downside of that is that if you're trying to estimate the average number of records, you're losing your noise. So you're populating everything else with an average, then your randomness is gone. The second method is interpolation. Interpolation is the method of constructing new data points from using some method. It could be an average of the value before and after. It could be just picking random variable, etc., etc. And it's very useful with the time series data. A single imputation, the other method that is actually very practical, well, I'm sorry, not practical, but popular, is partial deletion. So basically for let's say, for logistic regression, you need to have all values in your data set. So if you can't, or you're not sure about the business rules on how to replace your missing data, you just delete the entire observation. So that's called list-wise deletion and case-wise deletion. Pairwise deletion is deleting the case when it's missing a variable required for a particular analysis, but including that case in analysis for which all other variables are present. Very popular methods are hot deck and cold deck. Hot deck is basically drawing a random variable or random value from the same data set and populating it. Cold deck is the same as hot deck, but drawing that value from another data set. Regression imputation, basically you're trying to predict your what is your missing variable, what it could be. The word of caution here is replacing an average per category might also lead you to losing your noise. And finally, multiple imputations. Multiple imputations are, you can use the same methods as with a single imputation, like hot deck or cold deck, but you would use the multiple regression to populate those values, to randomly select different values, and then see if they, what results would it give you, and which ones would give you approximate picture of the randomness. So some of the advantages of multiple imputation is that it's flexible, can be used in different cases. In our specific case, it did not add any benefit, but nevertheless, you should be trying this as well when you're trying to replace and see what the results are. So, and just generally, which methods are more reliable and when. So mean substitution, for example, doesn't guarantee the relationships between the imputed and measured values. In other words, I've seen cases where missing values were replaced when over up to 30% of values was missing. Some other companies might not let you do that if you have 10% missing. So it really depends on your tolerance of that threshold. We then calculated this steps distribution per intensity, and you can see that intensity 1, it goes steeply downwards. And intensity 2 and again, intensity 1 is the slow pacing, etc. Intensities 2 and 3 are sort of within the normal range. So we tried three methods. For replacing missing values. We tried the mean value, interpolation, and the drawing from the distribution of existing values. So this is the code for the mean value. We're excluding the observations that are zeros or the outlier that is 500. And then we're getting the mean. It's pretty simple. The hot deck replacing the drawing the observations from the other population. You can use multiple methods. Again, you can replace the average between the two. You can replace it with the first value and last value, average of the first and last value. But basically, if your previous value was, let's say, 5, then it will replace all missing values with 5s until it encounters the next existing value. I'm sorry, that was not, this is hot deck. So the hot deck will take the distribution of existing values and plug it in. The formula that you use the formula is transform. Here it is. So the formula that you use to achieve that is transform in pandas. And finally, we're calculating the height, again, using the standard formula. Again, that might not be a perfect way to calculate the height, but this is just for to compare the results. So the results were that the original dirty data set had values, and again, those are just some of the outliers that we showed in the slide before. The dirty height was 3 feet. The average calculation replacement method gave us 511. The interpolation gave us 511, and the height distribution gave us 511. All three methods were pretty much gave us equal results, except for high interpolate varied a little bit from the others, but nevertheless they gave more realistic results. And this is the picture of Clint Eastwood. So the takeaways is that you need to fix data before you need to get it fixed. So you need to maintain data quality. Use dashboards and have a dedicated person work on the data quality. Data cleanup is important, is the second point. Your model can be very sophisticated and valid, but if you feed it a dirty data, you will not get a meaningful outcome. Use proper data types. Will save you a lot of times in the future, again, just like with converting the IDs. Always ask why and investigate your outliers, and data has a tendency to be used in unanticipated ways. So think about the variables that could possibly be used by other departments in the future, and also document your data sets. That'll make it easier for others to find what they need. If you have any questions, feel free to shoot me an email or to myself or Tanya about the presentation, or if you'd like a copy. And those are our Twitter. Follow us up. And that was my presentation.